An even larger source of CO2 is dying vegetation, from falling leaves, for example, in the autumn. But the biggest source of CO2 by far is the oceans. Carl Wunsch is Professor of Oceanography at MIT. He was also visiting Professor in Oceanography at Harvard University and University College London, and a Senior Visiting Fellow in Mathematics and Physics at the University of Cambridge. He is the author of 4 major textbooks on oceanography.
The ocean is the major reservoir into which carbon dioxide goes when it comes out of the atmosphere, or from which it is re-emitted to the atmosphere. If you heat the surface of the ocean, it tends to emit carbon dioxide. So similarly, if you cool the ocean surface, the ocean can dissolve more carbon dioxide.
So the warmer the oceans, the more carbon dioxide they produce, and the cooler they are, the more they suck in. But why is there a time lag of hundreds of years between a change in temperature and a change in the amount of carbon dioxide going into or out of the sea? The reason is that oceans are so big and so deep, they take literally hundreds of years to warm up and cool down. This time lag means the oceans have what scientists call a memory of temperature changes.
The ocean has a memory of past events running out as far as 10,000 years. So, for example, if somebody says, "Oh, I'm seeing changes in the North Atlantic," this must mean that the climate system is changing. It may only mean that something happened in a remote part of the ocean decades or hundreds of years ago, whose effects are now beginning to show up in the North Atlantic.
The current warming began long before people had cars or electric lights. In the past 150 years, the temperature has risen just over half a degree Celsius. But most of that rise occurred before 1940. Since that time, the temperature has fallen for 4 decades and risen for 3. There is no evidence at all from Earth's long climate history that carbon dioxide has ever determined global temperatures. But if CO2 doesn't drive Earth's climate, what does? The common belief that carbon dioxide is driving climate change is at odds with much of the available scientific data. Data from weather balloons and satellites, from ice core surveys, and from the historical temperature records. But if CO2 isn't driving climate, what is?
Isn't it bizarre to think that it's humans, when we're filling up our car, turning on our lights, that we're the ones controlling climate? Just look in the sky. Look at that massive thing, the sun. Even humans at our present 6.5 billion are minute relative to that.
In the late 1980s, solar physicist Piers Corbyn decided to try a radically new way of forecasting the weather. Despite the huge resources of the official Met Office, Corbyn's new technique consistently produced more accurate results. He was hailed in the national press as a super weatherman. The secret of his success was the sun.
The origin of our solar weather technique of long-range forecasting came originally from study of sunspots and a desire to predict those. And then I realised it was actually much more interesting to use the sun to predict the weather.
Sunspots, we now know, are intense magnetic fields which appear at times of higher solar activity. But for many hundreds of years, long before this was properly understood, astronomers around the world used to count the number of sunspots in the belief that more spots heralded warmer weather. In 1893, the British astronomer Edward Maunder observed that during the Little Ice Age, there were barely any spots visible on the sun, a period of solar inactivity which became known as the Maunder minimum. But how reliable are sunspots as an indicator of the weather?
Okay, boy.
I decided to test it by gambling on the weather through William Hill against what the Met Office said was a normal expectation. And I won money month after month after month after month. Last winter the Met Office said it could be or would be an exceptionally cold winter. We said, no, that is nonsense, it's going to be very close to normal. And we specifically said when it would be cold, i.e. after Christmas and February. We were right, they were wrong.
In 1991, senior scientists at the Danish Meteorological Institute decided to compile a record of sunspots in the 20th century and compare it with the temperature record. What they found was an incredibly close correlation between what the sun was doing and changes in temperature on Earth. Solar activity, they found, rose sharply to 1940, fell back for 4 decades until the 1970s, and then rose again after that.
When we saw this correlation between the temperature and solar activity or sunspot cycle lengths, then people said to us, okay, it can be just a coincidence. So how can we prove that it's not just a coincidence? Well, one obvious thing is to have a longer time series or different time series. Then we went back in time.
So Professor Friis Christiansen and his colleagues examined 400 years of astronomical records to compare sunspot activity against temperature variation. Once again, they found that variations in solar activity were intimately linked to temperature variation on Earth. It was the sun, it seemed, not carbon dioxide or anything else, that was driving changes in the climate. In a way, it's not surprising. The sun affects us directly, of course, when it sends down its heat. But we now know the sun also affects us indirectly through clouds. Clouds have a powerful cooling effect, but how are they formed? In the early 20th century, scientists discovered that the Earth was constantly being bombarded by subatomic particles. These particles, which they called cosmic rays, originated, it was believed, from exploding supernovae far beyond our solar system. When the particles coming down meet water vapor rising up from the sea, they form water droplets and make clouds. But when the sun is more active and the solar wind is strong, fewer particles get through and fewer clouds are formed. Just how powerful this effect was became clear only recently, when an astrophysicist, Professor Neer Shaviv, decided to compare his own record of cloud-forming cosmic rays with the temperature record created by a geologist, Professor Jan Weitzer, going back 600 million years. What they found was that when cosmic rays went up, the temperature went down. When cosmic rays went down, the temperature went up. Clouds and the Earth's climate were very closely linked. To see how close, you just flip the lines.
We just compared the graphs, just put them one upon the other, and it was just amazing. Jan Weitzer looked at me and says, we have very explosive data here.
I've never seen such vastly different records coming together so beautifully to show really what was happening over that long period of time.